Next is the laws of reflection and refraction. Experimental studies of the directions of the incident, reflected, and refracted rays at a smooth interface between two optical materials lead to the following conclusions. And in this figure, the material is A and B. It is either B glass or air or water. The incident, the refracted rays, and the normal to the surface. This is the normal line to the surface. And where's the surface? This is the surface that is touching. Ito yung surface na nagtatouch between A and B. They are all lie in the same plane. So, where's that plane? Dito. Okay? The plane of the three rays and the normal called plane of incident. It is perpendicular to the plane of the boundary surface between the two materials. This is the boundary of the two surfaces, so perpendicular si plane of incident. Ito siya. We always draw ray diagrams so that the incident, reflected, and refracted rays are in the plane of diagram. Okay? So, meron siyang point source ha, kung saan magpo-point out si incident ray papunta sa boundary material A and material B. Si reflected ray will always reflect what's been in here. So, sa refracted ray is magre-refract siya from this point also. Okay? Next is the angle of reflection, theta r, is equal to the angle of incident, theta a, for all wavelengths and for any pair of materials. That is the law of reflection. So the law of reflection is always have the same angle. Angle na incident ray from this normal line, theta a, is equals to theta r. This relationship, together with the observation that the incident and reflected rays and the normal all lie in the same plane, and is called law of reflection. Next, for monochromatic light, for example, is laser, and for a given pair of materials A and B, on opposite sides of the interface, the ratio of the sines of the angles theta A, the incident angle, and theta B is the refracted ray angle, where both angles measured from the normal to the surface is equal to the inverse ratio of the two indexes of refraction. So, normal siya sa kanyang, sabi is measured from the normal to the surface. So, ang normal is this one, from normal to the surface. So, si theta B is from this normal line up to the refracted ray. Si angle A, or the incident angle, and refracted angle, theta B, has this relationship. This is called sine of the angles. Sine ni angle incident over sine ni angle refracted is equals to index of refraction ni material B over index of refraction ni material A. So, the index of refraction will depend on what kind of material it is. In preceding lesson, we will have these values for index of refractions of various materials. This experimental result, together with the observation that the incident and refracted rays and the normal all lie in the same plane, is called the law of refraction, or Snell's law, after the Dutch scientist Wilbrod Snell. This is some doubt that Snell actually discovered it. The discovery that index of refraction is equals to C over V came much later. While these results were first observed experimentally, they can be derived theoretically from a wave description of light. First, a ray entering a material of larger index of refraction bend towards the normal. So, sa incident entering a material of larger index of refraction bends towards the normal. So, possible na since malaki yung index of refraction ni material B, kasi ang ray is nag-enter siya sa material of larger index of refraction, bends towards the normal. So, kung napapansin nyo, pag malaki yung index of refraction ni B, ang kaibahan niya dito is, maliit naman si B, napansin nyo yung kanilang incident angle ray is mas malaki kapag tumama siya sa mas malaking index of refraction material. Halimbawa si B is mas malaki kaysa kay A. And dito naman, si A is mas malaki kay B. So, yung index of theta, ang theta is maliit and then lalabas siya ng malaki. Okay? Dito malaki, lalabas siya ng maliit. So, halimbawa, if N is equal to, or the material A is equals to material B, there is no reflected and refracted. Bagkus, magkakaroon lamang ng incident light. Ito yung nangyayari sa air, sa laser, na ipo-point out mo lang sa normal air. Magkakaroon lang ng incident light. Okay? Equations 3.4 and 3.3 and 3.4 show that when a ray passes from one material into another material having a larger index of refraction, hence a slower wave speed, the angle theta b is bent toward the normal. Bent toward the normal. When the second material has a smaller index of refraction than the first material and hence a faster wave speed, the ray is bent away from the normal. The ray is bent away from the normal. Again, ito yung ating normal line ha. Normal line. No matter what the material on either side of the interface, in the case of normal incidence, the transmitted ray is not bent at all. For example is this one. In this case, theta A is equals to 0 and sine theta A is equals to 0. So from equation 3.4, theta B is also equal to 0. So the transmitted ray is also normal to the interface. Equation 3.2, where's our equation 3.2? Theta R is equals to theta A. Equation 3.2 shows that theta R2 is equal to 0. So the reflected ray travels back along the same path as the incident ray. Now the law of reflection explains why a partially submerged ruler or drinking straw appears bent. Light rays coming from below the surface change in direction at the air-water interface. So the rays appear to be coming from position above their actual point of origin. So, ito si tubig at ito si ruler. Why the ruler appears bent? Pag nakikita natin sa ating point of sight, si ruler is slightly bent. Okay? Kasi si NA natin is 1.33 and si NB is air, which is again 1. Si air is always has an index of refraction equal to 1 and mas malaki si NA. So, si ruler natin will have an incident angle or, I'm sorry, refracted angle okay, refracted angle slightly bent towards the normal. So, saan ang normal natin dito? Ito si observer, apparent position of end of the ruler, ang nakikita niya is slightly bent si ruler. Pero ang actual position ni ruler is andito. So, si NA is 1.33 compared kay NB na 1. Ang nangyari is, tulad nito, si material A is less or si material B has higher index of refraction than material A. So, ang kanyang refracted angle is bent towards the normal. So, saan ang normal natin? Ito ang ating normal. So, si angle niya is nagbend siya towards the surface of the water. Okay? An important special case is refraction that occurs at an interface between vacuum, for which the index of refraction is unity by definition and a material. When a ray passes from vacuum into material, so that NA is equals to 1 and NA is greater than 1 and B is greater than 1, the ray is always bent toward the normal. When a ray passes a material into vacuum so that NA is greater than 1 and NB is 1, the ray is always bent away from the normal. Again, this explains this figure 3.9. The laws of reflection and refraction apply regardless of which side of the interface the incident ray comes from. If a ray of light approaches the interface, like in the figure 3.9a or 3.9b, from the right than from the left, there are again reflected and refracted rays. These two rays, the incident ray and the normal to the surface, again lie in the same plane. Furthermore, the path of a refracted ray is reversible. It follows the same path when going from B to A as when going from A to B. So, it follows the same path regardless of, halimbawa, nandito naman si incident is galing naman dito, so it will follow this reverse pattern nito. Okay? Since malaki si NB kay NA, ang reverse pattern niya kapag nandito yung galing yung light is just the letter B. Figure 3.9, letter B. Again, always remember that if material A or material B is greater than material A, the angle of refracted is always bent towards the normal. And if material A less than or is greater than material B, the refracted is always greater than and will bend away from the normal. Okay. The intensities of the reflected and refracted rays depend on the angle of incidence, the two indexes of refraction, and the polarization of the incident ray. The fraction reflected is smallest at normal incidence, when theta is equals to 0 degrees. It is about 4% of an air-glass interface. This fraction increases with increasing angle of incidence to 100% at gazing incidence when theta is 90 degrees. It's possible to use Maxwell's equation to predict the amplitude, intensity, phase, and polarization states of the reflected and refracted waves. Such as analysis is beyond our scope, however. This index of refraction depends not only on the substance but also on the wavelength of the light. So, index of refraction depends not only again on the substance but also on the wavelength of the light. And the dependence on wavelengths is called dispersion. Indexes of refraction for several solids and liquids are given in table 3.1 for a particular wavelength of yellow light. This one.